Section 7.1, continuous random variables. So the goal here is to represent probability distributions for continuous variables. So far, you've looked at the discrete distributions, where the possible values of the random variable are natural numbers, okay, because they come from counting. But continuous probability distributions allow for any kind of fraction or decimal values. So they can be they have certain characteristics. I'm going to look at different kinds of continuous random variables here to start off with. But just before I do, I just want to explain that, what some examples of what are continuous variables, such as height or time, because time could be measured in fractions of a second. So we consider these kinds of variables to be continuous. So anything with a fraction or decimal value would be a continuous variable. Now, what do these distributions for continuous variables look like? Well, the first one is called a normal distribution, and it looks something like this. It has this bell shape to it, and it's a symmetrical shape about the mean. And we also describe it to have one hump. So it's a one hump, or what we call a unimodal distribution. So unimodal, just think of unimodal as one hump. So an example could be student grade averages in a class could be normally distributed. And a lot of things in scientific studies, nature, randomly occurring occurrences can be modeled usually using a normal distribution. So it's a very common distribution that we see in our study of mathematics. Another kind of distribution is a positively skewed distribution. So it would look something like this. So it's not symmetrical. It's still unimodal. The tail is pulled to the right, and more values are below the mean. So if your mean value is still here, you'd have more values below the mean. And if you recall this point right here, the top of the hump would still be considered your mode, because the y-axis represents your frequency. So the more frequent values, or in a sense. And the median would be somewhere in between the mode and the mean. Okay. And then we have a negatively skewed, which is just the opposite of the positively skewed. So it's not symmetric. The tail is pulled to the left, and more values are now above the mean value. So if my mean is here, there are more values above the mean. And we can also have bimodal graphs. Look something like this. Let me draw that nicely. So here's an example of a bimodal graph, because we have two humps. There's a hump here and there's a hump here. So this something like this could occur when you have two groups with different attributes. So an example would be adults' shoe sizes. So if one hump could be men, the other one could be women. And generally speaking, maybe men have larger feet than women. So that could be something that could be described or modeled by a bimodal distribution. Okay, so often you want to find probability that a variable falls in a particular range of values. The probability density function defines a continuous probability distribution for a given random variable. This kind of probability can be determined from the area under the distribution curve. And the probability that a random variable assumes a value within an interval is the area under the curve for that interval. So when we did discrete probability, looked at individual probability values and maybe added them up. When you're talking about continuous distributions, the probability that your event is within a certain range is now going to be the area under the curve. Okay, so let's look at some examples of what that might look like. So the driving time between Toronto North Bay is found to range evenly between 195 and 240 minutes. What kind of distribution is this? So we would call this distribution a uniform distribution, just like what we studied in the discrete. Uniform distribution. However, this is a continuous distribution, so it's going to be between 195 to 240. Time being the x-axis variable in minutes, And my y-axis will be the probability density. Okay. So you're going to have a little box here to show you our distribution. Now it ranges evenly. So it ranges evenly. That's why our box has a constant value for its probability density. Okay. So what does that mean? Well, the probability distribution must equal 1. The entire probability distribution must equal 1. So the area under this line here, all of this must equal 1. Okay, so let me write that here. So the probability distribution must equal 100% or 1. Okay, it can't be more than 100%. It can't be less. If it's less, then you're missing some ranges in your graph. So if the probability distribution must be 1, then the area under the curve must be 1. So the area under the curve must equal 1. Okay. So all driving times we know must be between 195 and 240 minutes. So the area of this rectangle here is going to be 240 minus 195. So the length times the width, or the height, I should say. So length times the height. So h must equal 1. So then what is that h value? If I solve for h, I would get 0.022. So that this y value right here would be 0.022. Now, what does that mean? We might be thinking, well, does that mean at any time I pick, you have a 2.2% probability? No, okay, because when you're talking about continuous distributions, you can't pick a single moment of time. Because if you picked a single moment of time, the area under the curve would be non-existent. It wouldn't exist. It's a sliver. It's like it's not, doesn't have a particular area, right? So when you talk about probabilities using continuous distributions, you're talking about an entire range. You have to talk about a range of values. A range of values will help us determine what shape we're looking for and help us find the area under the curve. Okay, so what is the probability that the drive will take less than 210 minutes? So if we let x represent, let me zoom in here so you can see a bigger text here. Let x represent the time it takes to drive between Toronto and North Bay. Okay, so the probability that x will be less than 210 is going to be equal to the base times the height. If I go back to my graph, 210 would be, where would 210 be? Maybe somewhere around here. 210. Okay, so I'm looking for this area right there, right? That area right there. So the base is going to be 210 minus 195. This is the graph begins at 195, multiplied by the height, which we already found to be 0.022, and that equals 0.33. So the probability, my conclusion here, therefore, the probability the drive takes less than 210 minutes is 33%. So again, we're looking at the area under the curve. That's where we can get the probabilities. If I had asked, what's the probability that it would take exactly 210 minutes, I wouldn't be able to determine that using the graph. So it's not possible. Continuous probabilities only work on ranges. Continuous probability only works on ranges. Okay, so here's a question I'd like you to try. Pause the video. Your turn. Okay, pause the video. Try to answer the question here about Chris working at a tire store. When you unpause the video, I'll give you the solution. Okay, so hopefully you had a chance to check it out. So here's what the probability distribution would look like. Chris would be here from 8 to 12 minutes. All the times are equally likely. And from 8 to 12 minutes, that height would be so 100% divided by 4 minutes between 8 and 12, giving me a value of 0.25 for my probability density. So this would be 0.25. So the probability that Chris changes a given tire in less than 9 minutes, so the probability that the tire changes less than 9 minutes is equal to 9 minus 8. 8 is the lower end of my interval, and I multiply that by 0.25, and that gives me 0.25, or 25%. Probability that Chris takes between 9 and 11.5 minutes to change a tire, so now we're looking at the probability that 9 is less than x and x is less than 11.5, equal to 11.5 minus 9. So the base is just the two intervals we're restricting ourselves here, multiplied by 0.25, and that equals 62.5%. Okay, let's look at frequency tables, frequency histograms, and frequency polygons. So below are student scores in a data management examination. Can you use the data in the table to determine whether the data seems to follow a uniform distribution? Well, just by looking at the table, there's no way for me to tell. It's kind of difficult to analyze, so it's not obvious. If the distribution is uniform, you can't really say from just looking at the table of values. Same idea, you can't really find the mean exam mark just by inspection. You have to do some kind of calculation. So we're going to construct a frequency table here to help us find this distribution and the mean value. So if you tallied up all of these numbers here, well, what you would get is you'd have 1 for the interval between 30 and 40. You would also have 1 for 40 to 50. And you'd have 3 tick marks here for 50 to 60. Here you'd have 8 tick marks, so 1, 2, 3, 4, 5, 6, 7, 8. You'd count 10 for the next one, 5 for the next one, and 2 for the next one. So if I took all of these values and I placed them in their appropriate bins here, and the score ranges and intervals, I would get a frequency table that looks like this. Okay. Now, relative frequency, what relative frequency is taking every single frequency value and dividing it by the total frequency. Okay, so how many numbers do I have here? Well, I have 30 numbers. If I add up all of these frequencies, I would have a total of 30. So relative frequency would simply be taking the frequency, 1, divided by 30, and I would get a value of 0.033. And you can treat relative frequency like a probability value, which is what we're going to be doing. So 3.3%. So that would similarly for the next one, it would be the same number, 0.033, which is also 3.3%. Next one, 3 divided by 30 is equal to 0.10, which is 10%. And if you do the same thing for the rest, you get 0.267, 0.333, 0.167, and 0.067. I'm just going to write down the percentage values here on the side as well. So 26.7%, 33.3%, and 16.7%, and 6.7%. Now, if you add up all these percentages, you should get 100%. There could be tiny differences because of rounding, but it should be on the mark pretty much. All right, so part C, how does a frequency table help you analyze the raw data from a sampling experiment? Well, the frequencies vary from 1 to 10. So what does that suggest? That distribution is not uniform. So the distribution here, I'm going to write that the distribution is not uniform because frequencies are different. And the mean value, so look at the most common value. It's going to be likely in this bin range between 70 and 80. So I'm just going to say the midpoint. The midpoint of that is 75. So the midpoint would be about 75%. The mean examination mark is 75%. Okay, let's move on to the next part. So use the frequency table to draw the frequency histogram. So the histogram is just basically our distribution. What's our distribution going to look like? So I'm going to just write down the bins here on the side. So we have 30 to 40, 40 to 50, 50 to 60, 60 to 70, 70 to 70. I should be rewriting this properly, actually. So if I'm going to be including the endpoints, I would make sure they start from the next one. So I'm going to go from 30 to 39, 40 to 49, 50 to 59, 60 to 69, 70 to 79, 80 to 89, 90 to 99, and we don't have any hundreds up there, but if we did, we could probably just make another one there, but we don't. So I'm going to also divide the y-axis here. So we'll count by 10%, so 0.10, 0.20, 0.30. We don't have anything that goes up to 40%, so we're fine there. Now, if I take every single frequency value and I plot them, so in the first one, I will have a frequency of 3.3%, so somewhere about here. I'm using the percentages now, right? So 3.3%, or the relative frequency of 0.033. So I'm plotting the relative frequency. It may help to actually label your sides too. So relative frequency. And 40 to 49 is also 3.3%. 50 to 59 is 10%. And 60 to 69 is 26.7%. So maybe right about above here a little bit. I'm just kind of freehanding this, but you should make sure you use proper tools to draw a straight graph. 70 to 79 is 33.3%, so somewhere around here. And 80 to 89 is at 16.7%, so we're back down here. And then 90 to 99 is 6.7%, so maybe just a smidge above the 5. Okay, this is a rough estimate of a rough drawing of what the distribution would look like. And it's important to note that we use relative frequencies because it would allow me to say that all of these, the area under this graph would be adding up to 100% or equal to 1. Had I used absolute frequencies, that would not be the case. Okay, so the shape of the frequency polygon gives us an indication of the shape of the probability of distribution. And the total area under the frequency polygon is not equal to 1, which is why we use the relative frequency polygon. So, I'm sorry, I'm mixing up something. So the frequency polygon is not the graph. The frequency polygon, one more thing. Well, actually, what I wrote here was correct. It's not equal to 1, but I didn't explain what the frequency polygon is. The frequency polygon is if you took the midpoint of every single interval and connect them by drawing a polygon. So I'm just going to use straight lines here. Oh, change the color. Oops. So let's make that red. Straight lines. So red. Another one. Draw another one. And another one. So you can keep going until you reach the end. So I'm just connecting the midpoints of every interval at the value of the relative frequency. And you get this, what I see in red here is this frequency polygon. So the area under this frequency polygon is not going to be 1 because you have all this extra spacing and overlapping bars here. So it's not going to equal to 1. So you cannot calculate probabilities using areas under frequency polygon. So what you do need to use is a probability distribution. So you need to use a probability distribution using the relative frequencies to determine the probabilities. And that ends this lesson.